And it looks like we're live. Stream looks good at 1080p. Audio seems to be going out. All right. And my watch is trying to listen to me. That's great. So last night was interesting. I had forgotten to check the meetup schedule, and yesterday was the Boulder the Boulder Denver Rust meetup, and they're doing this every other month schedule. Well, last night was this month's turn for the Boulder Denver Rust meetup to be in Denver. So it was really awesome to hang out with like a bunch of other Rust developers, some of them learning like me, and we had 4 people who were writing Rust professionally at companies for money, which was really awesome. And the talk was about how to bring Rust into the enterprise workplace and sort of how to convince your teams that Rust is a safe, awesome language to use, but then also how to end up then making it fun, awesome, safe to use, and high quality with your team. And some of those things are not Rust related, they're just programming culture related. That would be things like test-driven development whenever you can. It could also be from the management level, not pushing developers to put out code before it has been properly tested and vetted, to have code reviews by your peers, to have a style sheet and a style guide that you adhere to have an entire ecosystem where when you push, it will deploy to your test servers. Things like that, which aren't necessarily set to Rust, but Rust does make like test-driven development a lot easier by not making you pull in new libraries. And also, apparently, it was one of the questions was the company afraid that it wouldn't be able to hire developers? And they had a really interesting answer, which was to bring up the point that they were in Seattle, like close to Seattle, close to Washington. I guess Seattle, Washington State. They knew that they were in close proximity to Microsoft, to Amazon, and to a bunch of other of these startups. They needed to compete for developers, and one of the big things that they found going for them was a lot of them wanted to work on Rust, and therefore would be willing to not go work for Microsoft or Amazon or other places to work for them and bring their talents there, as long as they were allowed to learn Rust. So I thought that was really a really interesting idea of like how to get high talent into your workplace. All right, so I mean that was fun. I don't know what the in 2 months we'll have it again here in Denver, and I'm continuing to plan on go to them. If I remember that it's like the next day, I'll try to like maybe get a series of questions or something to ask for some of the other developers, so then we can maybe get some awesome Q&A going. Until then, let's continue on with the book. So last time we're in the middle of object-oriented programming features of Rust. Oh, did I fail to? I could swear that I had pushed that up, but maybe I didn't. Let's go check to make sure that I actually do have the link to where we're really going. So yeah, this is completely different. Adding the improvement. Okay, so then that's the problem. I just needed to push up. Apparently I forgot to do that. So refresh. Let's try this. Much better. Adding the approve method that changes the behavior of content. The approve method will be similar to the request review method. It will set state to the value that the current state says it should have when that state is approved, as shown in listing 1716. Okay, so we have our implement for the blog post. Miguel, good morning. Hey. We're making a public function approved, takes mutable self. We do the iflets, self.state.take. Okay, self state some approve. Okay, so basically, if we're in the right state, basically we're going to run this take and then if it's truthy, or if it exists really, then we're going to run the approve. Trait states. We're going to have request approve review and approve. These are both going to return boxes. We have a draft structure, implement state for draft, function approve. So here's this function being implemented now, which takes in a box right here. So we're going to return a box of state. So this is Miguel, I don't know if you saw yesterday's, but this is a pattern where we could basically say it's a trait box where it's basically holding any, like almost a generic, as long as it's this state, we can store something in there. It's like a string wouldn't work because a string doesn't have the state trait. Then we just return self. Pending review, implement state for pending review. So we're implementing the state for everything. Yeah, you checked the VODs? Awesome. Struct published, state for published. And of course, they're all doing slightly different things. And I guess like that's the key to this is we're saying like we have this trait, but the trait will do different things depending upon each of them. So it's an object-oriented way. It's kind of our way of overwriting. Like we define in here what it's gonna have, but we don't really dictate how it's gonna work. We just write the contract where we say it's gonna take in self, which is a box that holds self, and we're gonna return a box that requires something that has a certain state. And that's it. We add the approve method to the state trait and add a new struct that implements state, the published state. Similar to request review, if we call the approve method on a draft, it will have no effect because it will return self. When we call approve on pending review, it returns a new boxed instance of the published struct. The published struct implements the state trait, and for both the request review method and the approve method, it returns itself, because the post should stay in a published state in those cases. Now we need to update the content method on post. If the state is published, we want to return the value in a post content field. Otherwise, we want to return an empty string slice, as shown in listing 1717. So implement post, public function, so we have our content, which is going to return a string slice. We then dive into self state as ref to like get that out, so get the reference, unwrap it so we get the content. Then we run the content function from above and pass it the reference to self so that it can then, and no semicolon. So whatever the result of the content is, so that's getting the blog post, it returns it. But of course, This only works if we're in a published state. Because the goal is to keep all these rules inside the structs that implement state, we call content method on the value of state in state and pass the post instance, that is, self, as an argument. Then we return the value that is returned from using the content method on the state value. We call the asRef method on the option because we want a reference to the value inside the option, rather than ownership of the value. Because state is an option box state, when we call asRef, an option box state is returned. If we didn't call asRef, we would get an error because we can't move state out of the borrowed self of the form of the function parameter. We then call the unwrap method, which we know will never panic because we know the methods on post ensure that state will always contain a sum value when those methods are done. So we know that, and we can be confident about it because we wrote it. Now there is something to be said about that. We could, like when we're developing, we could also just develop very defensively and just say we don't even trust ourselves to write that properly. We could create a bug where we don't do what we're supposed to do. And this is where good testing will prevent that. But yeah, like different ways to think about it. This is one of the cases we talked about in the cases when you have more information than the compiler section of chapter 9, when we know that a none value is never possible, even though the compiler isn't able to understand that. At this point, when we call content on the box state, deref coercion will take effect on the ampersand in the box, so the content method will ultimately be called on the type that implements the state trait. That means we need to add content to the state trait definition, and that is where we'll put the logic for what content to return depending on which state we have, as shown in listing 1718. So here we have the trait state, function content. We're going to have to use lifetimes here. So A, bring in self, post, because it's a reference to the post, we have to give it this lifetime of A, and we're returning a reference to the string, so that's A as well. This is a simple one. I think the only reason we need it is because we have the self here. And it will, like, automatically the borrow checker would say, well, we have A, and then we have B here, and it doesn't know which one to return with. Okay, so struct published, implement state for published, function content, lifetime A, self. So it's, I mean, obviously exactly the same. The contract has to be the same, and then we're going to return a reference to post.content. We add a default implementation for the content method that returns an empty string slice. That means we don't need to implement content on the draft and pending review structs. The publish struct will override the content method and return the value in post.content. Note that we need lifetime annotations on this method. As we discussed in chapter 10, we're taking a reference to a post as an argument and returning a reference to part of the post. So the lifetime of the return reference is related to the lifetime of the post argument. And we're done. All of listing 1711 now works. We've implemented the state pattern with the rules of the blog post workflow. The logic related to the rules lives in the state objects rather than being scattered throughout post. Trade-offs of the state pattern. We've shown that Rust is capable of implementing the object-oriented state pattern to encapsulate the different kinds of behavior a post should have in each state. The methods on post know nothing about the various behaviors. The way we organized the code, we have to look in only one place to know the different ways a published post can behave. The implementation of the state trait on the published struct. If we were to create an alternative implementation that didn't use the state pattern, we might instead use match expressions in the methods on post, or even in the main code that checks the state of the post and changes behavior in those places. That would mean we would have to look in several places to understand all the implications of a post being in a published state. This would only increase the more states we added. Each of those match expressions would need another arm. With the state pattern, the post methods and the places we use post don't need match expressions. And to add a new state, we would only need to add a new struct and implement the trait methods on that one struct. The implementation using the state pattern is easy to extend, add more functionality. To see the simplicity of maintaining code that uses the state pattern, try a few of these suggestions. So it's add a reject method that changes the post state from pending review to back to draft, require 2 calls to approve before the state can be changed to published, allow users to add text content only when a post is in the draft state. A hint, have the state object responsible for what might change about the content, but not responsible for modifying a post. I believe, so these ones would be simple functions that would be added in using implement. This one, I believe, would require 2 functions. Well, I would probably do it with 2 functions. Basically, you have the trait function that you're going to basically be doing that on. But it's going to call another function to find out, are you okay with that? That way, it doesn't have too many things that's doing in there. One downside of the state pattern is that because states implement the transitions between states, some of the states are coupled to each other. If we add another state between pending review and published, such as scheduled, we would have to change the code in pending review to transition to scheduled instead. It would be less work if pending review didn't need to change with the addition of a new state. But that would mean switching to another design pattern. Another downside is that we've duplicated some logic. To eliminate some of the duplication, we might try to make default implementations for the request review and approve methods on the state trait that return self. However, this would violate object safety because the trait doesn't know what the concrete self will be exactly. We want to be able to use the state as a trait object, so we need its methods to be object safe. Other duplication includes the similar implementations of the request review and approve methods on post. Both methods delegate to the implementation of the same method on the value in the state field of option, and set the new value of the state field to the result. If we had a lot of methods on post that follow this pattern, we might consider defining a macro to eliminate the repetition. See Appendix D for more on macros. By implementing the state pattern exactly as it's defined for object-oriented languages, we're not taking as full advantage of Rust's strengths as we could. Let's look at some changes so we can make some changes we can make to the blog crate that can make invalid states and transitions into compile time errors. So what they were just talking about there was like the reuse of code problems and some of the other things. And in traditional object-oriented, you would basically have the classes and have classes extend from other classes, so you could put shared functions and properties on the topmost class. But the problem that the book yesterday talked about was, and it's something that I've seen a lot of people have run into. If you end up doing that, it's great when you first write the code, but as things go on and you start making changes to it, it becomes very tightly interwoven because, oh, well, we need to add this one thing, but we're either going to add it to the top level where everything gets it, even if we don't necessarily want it to, or we're going to come down and add it to like something else. But then we have to repeat it, and then you end up with that duplication of code. So I'm starting to lean more and more in duplication of code is okay, but as long as everybody understands what that duplication of code is. I guess because we're creating these interfaces for this blog that defines this is in general what the signature of the function is going to look like, but the that how it's implemented is going to be different. I like that a lot more. But with traditional object-oriented, if you forgot to override it, you could be in trouble because you'd get the default behavior, which you wouldn't necessarily want. And the compiler would be fine because it exists there. So, I don't know. In recent years, I've been more and more sort of heading more towards the functional side of things rather than the object-oriented. Not necessarily going full hog into the mathematical functional side, but more of just like with the ideology of, hey, let's try not to do too many classes. We could just create structs and return them from the object. That was a long sneeze in the making. All right, encoding states and behavior as types. We'll show you how to rethink the state pattern to get a different set of trade-offs. Rather than encapsulating the states and transitions completely so outside code has no knowledge of them, we'll encode the states into different types. Consequently, Rust's type checking system will prevent attempts to use draft posts where only published posts are allowed by issuing a compiler error. Let's consider the first part of main in listing 1711. So we have main let mute post equals post new, post add text, I ate a salad for lunch today, and then we're assert equal that we can't actually get the content yet because it's in a draft state. We still enable the creation of new posts in the draft state using post new and the ability to add text to the post content. But instead of having a content method on a draft post that returns an empty string, we'll make it so draft posts don't have the content method at all. That way, if we try to get a draft post content, we'll get a compiler error telling us the method doesn't exist. As a result, it'll be impossible for us to accidentally display draft post content in production, because that code won't even compile. Listing 1719 shows the definition of a post struct and a draft post struct, as well as methods on each. Okay, so our post struct, content string, our draft post, content string, implement post, so we have our new. So our new on the post, it ends up just returning a draft post and setting the content to that. And what's interesting is that, then we have this public function content that returns a reference to this content string. But of course it doesn't exist because we didn't, like in new, it created a draft post. I'm not sure how much I really like this. And I feel like weird about the previous pattern too, because I feel that there's a lot of sort of like magic that we're writing in behind the scenes, that somebody who's implementing it, they go to create a new post, but they create a new draft. But there was nothing about saying, oh, I want to create a draft. That feels less explicit to me. Both the post and draft post structs have a private content field that stores a blog post text. The structs no longer have the state field because we're moving the encoding of the state to the types of the structs. The post struct will represent a published post, and it has a content method that returns the content. We still have a post new function, but instead of returning an instance of post, it returns an instance of draft post. Because content is private and there aren't any functions that return post, it's not possible to create an instance of post right now. The draft post struct has an add text method, so we can add text to content as before, but note that draft post does not have a content method defined. So now the program ensures all posts start as draft post, and draft posts don't have their content available for display. Any attempt to get around these constraints will result in a compiler error. Yeah, like I'm not also, like thinking about the blogs that I've used, I want to see the draft. But I guess like this is also because we're going through a kind of what is the words that I'm looking for? Basically, we're doing this as an example of object-oriented style programming, not necessarily creating like a real blog with the real features that we'd actually want. Implementing transitions as transformations into different types. So how do we get a published post? We want to enforce the rule that a draft post has to be reviewed and approved before it can be published. A post in a pending review state should still not display any content. Let's implement these constraints by adding another struct. Pending review post, defining the request review method on draft post to return a pending review post, and defining an approve method on pending review post to return a post as shown in listing 1720. So we have our draft post, and now this is going to implement a new function, request review, which is going to return a pending review post, which will have the content. So we're now going to move the content into pending review post. In pending review post, we have a string, and then we implement this pending review post. There it is. Pending review post. Okay. Implement review. I guess that's setting that. It kind of feels weird that they're not using like a new function with that also. Okay, so public function approve, self, post, and the post has content self. So basically we're just, well, so if we approve, we're then going to return a full post. State pattern, yeah, like it's basically a state machine, like, or rather, we're going through like different ways of doing state management and state patterns and state machines and all the fun things to do with state. The request review and approve methods take ownership of self, thus consuming the draft post and pending review post instances and transforming them into a pending review post and a published post, respectively. This way, we won't have any lingering draft post instances after we've called request review on them, and so forth. The pending review post struct doesn't have a content method defined on it, so attempting to read its content results in a compiler error, as with draft post, because the only way to get a published post instance that does have a content method defined is to call the approve method on a pending review post. And the only way to get a pending review post is to call the request review method on a draft post. We've now encoded the blog post workflow into a type system. But we also have to make some small changes to main. The request review and approve methods return new instances rather than modifying the struct they're called on. So we need to add more let post equal shadowing assignments to save the return instances. We also can't have the assertions about the draft and pending review post contents be empty strings, nor do we need them. We can't compile code that tries to use the content of posts in those states any longer. The updated code in main is shown in listing 1721. Okay, so we're bringing in the blog itself and the post. So function main, let mute post equals post new. Let's create an empty new post. We then add the text. Let post equals, so post request review, and then let post equals post.approve. And so the reason why we're doing shadowing here is because this post is done. Like as soon as we run request review, the content in the struct in like, well, I guess like post never really existed for us. It immediately gave us a draft, but the draft was consumed as soon as we run this method on it because it creates a what is it? The request approval struct. We moved the content into there, which is why we might as well shadow. That we don't even want the ability to run this to get this variable anymore. Then we do the exact same thing with approve, which means now we have an actual real post in post. And then we have our final assert. The changes we needed to make to main to reassign post mean that this implementation doesn't quite follow the object-oriented state pattern anymore. The transformations between the states are no longer encapsulated entirely within the post implementation. However, our gain is that invalid states are now impossible because the type system and the type checking that happens at compile time. This ensures that certain bugs, such as display of the content of an unpublished post, will be discovered before they make it to production. Try the tasks suggested for additional requirements that we mentioned at the start of the section on the blog crate as it is after listing 1720 to see what you think about the design of this version of the code. Note that some of the tasks might be completed already in this design. We've seen that even though Rust is capable of implementing object-oriented design patterns, other patterns, such as encoding state into the type system, are also available into Rust. These patterns have different trade-offs. Although you might be very familiar with object-oriented patterns, rethinking the problem to take advantage of Rust's features can provide benefits, such as preventing some bugs at compile time. Object-oriented patterns won't always be the best solution in Rust due to certain features, like ownership, that object-oriented languages don't have. So, I mean, this is pretty much talking about how I feel about things like this. And I guess like my personal history with object-oriented programming was first with Python. You know, I learned object-oriented programming there. Even though you don't need it, I kind of wasn't aware of that because the teachers that I had just like went straight to classes, and I remember being very confused when I would just use classes for everything, even like exiting the program, and then my code reviewers would say like, you don't need to do that there, and I'm like, oh, I don't, and then like sort of think about it more of like, oh well, it's a language that I don't like. Not where you have to use classes for everything. It's where you can. And I sort of get that feeling here in Rust. It's also very similar in JavaScript, which allows you to use object-oriented design patterns, but it also allows you to use functional design patterns. And I'm getting a lot of that leaning here too, which is, oh, I want to use functional design patterns. Great, I'm going to start using that. In the end, it's like the best thing is probably to use a mix. Like we have the ability to use both. Let's not relegate ourselves to one side or the other. Let's just do it all. When it makes sense for us, we can do this object-oriented state pattern. To me, this feels a little bit better, but not quite there yet. If I was doing this, I would design it based upon the main function here. And so I would probably say like, look, I don't want to even create a post. Like I would just say post, you're not allowed to create a post at all. I wouldn't even have a new, like if I had a new function, it wouldn't be allowed to be created from main. But I create a new draft. And so I could say like let mute draft equals draft new. I could add the text into that. And then I could say like, hey, I want to request the review. The problem is like these functions aren't doing what we want them. Like they're not doing anything. In reality, we would need to get the text back from the draft so we can actually review it and then approve it. And then it would go into like a pending review type. I might as well put that into its own variable that names what's happening. And then we can approve it, and then we can get the content from the post. That's sort of like, so very close to this method, but slightly different. Unnamed outsider, you agree? Also, I didn't say it, but good morning. Welcome to the stream. Okay, so we did that. Summary. No matter whether or not you think functional OP mixes good stuff. Yeah, I really like the idea. Well, I really like the idea of not feeling that I have to extend with object-oriented. And I get the great ability of blueprints, without the ability of like the monkey holding the banana with the jungle when you try to bring everything in. No matter whether or not you think Rust is an object-oriented language, after reading this chapter, you now know that you can use trait objects to get some object-oriented features in Rust. Dynamic dispatch can give your code some flexibility in exchange for a bit of runtime performance. You can use this flexibility to implement object-oriented patterns that can help your code's maintainability. Rust also has other features, like ownership, that object-oriented languages don't have. An object-oriented pattern won't always be the best way to take advantage of Rust's strengths, but is an available option. Next, we'll look at patterns, which are another of Rust's features that enable lots of flexibility. We've looked at them briefly throughout the book, but we haven't seen their full capability yet. Let's go. All right, so we're on to chapter 18, patterns and matching. Patterns are a special syntax in Rust for matching against the structures of types, both complex and simple. Using patterns in conjunction with match expressions and other constructs gives you more control over a program's control flow. A pattern consists of some combination of the following. So literals, destructured arrays, enums, structs or tuples, variables, wildcards, and placeholders. Right, I would say like, okay, definitely a combination, because on their own, that doesn't really make sense. These components describe the shape of the data we're working with, which we then match against values to determine whether a program has the correct data to continue running a particular piece of code. To use a pattern, we compare it to some value. If the pattern matches the value, we use the value parts in our code. Recall the match expressions in chapter 6 that used patterns, such as the coin sorting machine example. If the value fits the shape of the pattern, we can use the named pieces. If it doesn't, the code associated with the pattern won't run. This chapter is a reference on all things related to patterns. We'll cover the valid places to use patterns, the difference between refutable and irrefutable patterns, and the different types of pattern syntax that you might see. By the end of the chapter, you'll know how to use patterns to express many concepts in a clear way. Let's dive in. All the places patterns can be used. Patterns pop up in a number of places in Rust, and you've been using them a lot without realizing it. Well, I think I realized that because every single time we used one, the book also said, and wait until chapter 18, we'll talk more about the pattern that you used. This section discusses all the places where patterns are valid, so match arms. As discussed in chapter 6, we use patterns in the arms of match expressions. Formally, match expressions are defined as the keyword match, a value to match on, and one or more match arms that consist of a pattern and an expression to run if the value matches that arm's pattern, like this. So, right, I mean, we've been doing that. We've been doing that a lot. A run requirement for match expressions is that they need to be exhaustive, in the sense that all possibilities for the value in a match expression must be accounted for. One way to ensure you've covered every possibility is to have a catch-all pattern for the last arm. For example, a variable name matching any value can never fail and thus covers every remaining case. That's, I think, the underscore. A particular pattern underscore will match anything, but it never binds to a variable, so it's often used in a latch match arm. The underscore pattern can be useful when you want to ignore any value not specified. For example, we'll cover the underscore pattern in more detail in the ignoring values in a pattern section later in the chapter. So actually that's good to know, because on my own, we were trying to like go down a side path in one of the examples a while back, and we did use I did use underscore to just try to catch anything, but then go ahead and print it, and the compiler was really unhappy with that and said like, no, you're ignoring that. You don't care. You clearly don't care about it because you used underscore. Conditional if-let expressions. In Chapter 6, we discussed how to use if-let expressions, mainly as a shorter way to write the equivalent of a match that only matches one case. Optionally, if-let can have a corresponding else containing code to run if the pattern in the if-let does not match. Listing 18.1 shows that it's also possible to mix and match if-let, else-if, and else-if-let expressions. Doing so gives us more flexibility than a match expression in which we can express only one value to compare with the patterns. Also, the conditions in a series of if-let, else-if, else-if-let arms aren't required to relate to each other. The code in listing 18.1 shows a series of checks for several conditions that decide what the background color should be. For this example, we've created variables with hard-coded values that a real program might receive from user input. All right, so let's take a look. We have function main, let favorite color equals, so it's an option string, so it's the none. So it's the none part of the enum. Let is Tuesday equals false. Let age equals result. U8 that 34.parse. Okay, so we're not caring about the error because we're not. I mean, 34 is just going to become the number. If let sum color equals favorite color, so it's going to come into here, and if it is set, so it's a sum, then the result will go into the color. However, it doesn't because we have a none, so it's going to actually skip and not run this code, and we're going to go on to the next. Else if is Tuesday. Well, that's false, so we're not going to run this one. So else if let okay age, which basically this returns a sum, then age result 30. I guess this is setting what the type is going to be. And this is going to be the variable name. So age is a result, and this has become the number that goes into age. Then we check inside of here if age is greater than 30, which it is. Then we print using purple as a background color. Otherwise, using orange as a background color. That's such a strange example for like a color. Like if you're older than, I guess purple is my favorite background color. Else print line using blue as the background color. So that's if we don't have, if this was an error or had like a none in here. If the user specifies a favorite color, that color is the background color. If today is Tuesday, the background color is green. If the user specifies their age as a string, and we can parse it as a number successfully, the color is either purple or orange, depending on the value of the number. If none of these conditions apply, the background color is blue. This conditional structure lets us support complex requirements with the hard-coded values we have here. This example will print using purple as the background color. You can see that if-let can also introduce shadowed variables in the same way that match arms can. The line if-let okay age equals age introduces a new shadowed age variable that contains the value inside the okay variant. This means we need to place the if age is greater than 30 condition within that block. We can't combine these two conditions into if-let okay age equals age and age is greater than 30 because this one would run first and set age and then we'd lose it. The shadowed age we want to compare to 30 isn't valid until the new scope starts with the curly bracket. Oh, okay, never mind. So we'd still have the other age here. It would be a result. The downside of using if-let expressions is that the compiler doesn't check exhaustiveness, whereas the match expression, it does. If we omitted the last else block, and therefore missed handling some cases, the compiler would not alert us to the possible logic bug. while-let conditional loops. Similar in construction to if-let, the while-let conditional loop allows a while loop to run for as long as a pattern continues to match. The example in listing 18.2 shows a while-let loop that uses a vector as a stack and prints the values in a vector in the opposite order in which they were pushed. So we have let mute stack equals a new vector. We then push 1, 2, 3 to the stack. While let sum, the top of the stack equals stack.pop, and so pop is from the end, so that would be the last one, 3, goes into top. So while this is possible, print line the top. And so it'll loop again, and then we'll get 2, and then we'll get 1, and then it'll come out, and there won't be a result, or it won't be a sum that returns out of it. It'll be something else, and so therefore the while that will end. This example prints 3, 2, and then 1. The pop method takes the last element out of the vector and returns some value. If the vector is empty, pop returns none. The while loop continues running the code in its block as long as pop returns some. When pop returns none, the loop stops. We can use the while let to pop every element off our stack. For loops. In chapter 3, we mentioned that the for loop is the most common loop construction in Rust code, but we haven't yet discussed the pattern that for takes. In a for loop, the pattern is the value that directly follows the keyword for. So in for x and y, the x is the pattern. Listing 18.3 demonstrates how to use a pattern in a for loop to destructure or break apart a tuple as part of the for loop. So we have done some of the destructuring, specifically right here in this example in the enumerate, because that returns to us a tuple where the first value is index and the second value is the actual value. We use the enumerate method to adapt an iterator to produce a value that is the value's index in the iterator placed into a tuple. The first call to enumerate produces the tuple 0a. When this value is matched to the pattern index value, index will be 0 and value will be a, printing the first line of the output. Let statements. Prior to this chapter, we had only explicitly discussed using patterns with match and if let. But in fact, we've used patterns in other places as well, including in let statements. For example, consider the straightforward assignment, variable assignment with let. So let x equals 5. Throughout this book, we've used let like this hundreds of times, and although you might not have realized it, you are using patterns. More formally, a let statement looks like this. So let pattern equals expression. In statements like let x equals 5, with a variable name in the pattern slot, the variable name is just a particular simple form of a pattern. Rust compares the expression against the pattern and assigns any names it finds. So in the let x equals 5 example, x is a pattern that means bind what matches here to the variable x. Because the name x is the whole pattern, the pattern effectively means bind everything to the variable x, whatever the value is. To see the pattern matching aspects of let more clearly, consider listing 18.4, which uses a pattern with let to destructure a tuple. So, it's the same thing we saw in the for loop, where we just say, okay, we're going to say the first one, so 1 in this case, goes into x, this goes into y, and it's just positional, right? So like the first thing in the parentheses will go into the first thing here. Here we match a tuple against a pattern. Rust compares the value 1, 2, and 3 to the pattern x, y, and z, and sees that the value matches the pattern. So Rust binds 1 to x, 2 to y, and 3 to z. You can think of this tuple pattern as nesting 3 individual variable patterns inside it. If the number of elements in a pattern doesn't match the number of elements in the tuple, the overall type won't match, and we'll get a compiler error. For example, Listing 18.5 shows an attempt to destructure a tuple with 3 elements into the 2 variables, which won't work. Right, because the compiler is requiring us to do this. Now, other languages are not quite as like rough on it. This chapter seems very out of place considering the last couple of chapters. This chapter kind of feels like a an appendix, like just like more information to use, but we've kind of done all these so far. If we wanted to ignore one or more of the values in the tuple, we could use underscore or dot dot, as you'll see in the ignoring values in the pattern section. If the problem is that we have too many variables in a pattern, the solution is to make the types match by removing variables so the number of variables equals the number of elements in the tuple. So that's where it gets interesting, where we can use that underscore here. And then dot dot allows us to skip an unknown, to skip a certain amount, I believe. Or like skip the rest of them. Where you can say like x dot dot and we will skip 2 and 3 and only get 1. We'll just reach the end of this page and then we'll call it a morning. Function parameters. Function parameters can also be patterns. The code in listing 18.6, which declares a function named foo that takes one parameter named x of type i32, should by now look familiar. So function foo x i32, then our code goes here. The x part is a pattern. As we did with let, we could match a tuple and a function's arguments to the pattern. Listing 18.7 splits the values in a tuple as we pass it to a function. Okay, so print coordinates, it's a reference to a tuple that dereferences x and y out of these types, which is a reference tuple i32, i32. So that works, but it doesn't really look like we're gaining anything out of here besides the fact that we're getting a tuple, and then we could do the dereferencing right on the next line. This code prints current location 3, 5. The values 3 and 5 match the pattern x and y. So x is the value 3 and 5 is the value 5. We can also use patterns in closure parameter lists in the same way as in function parameter lists, because closures are similar to functions as discussed in chapter 13. Well, they share the same trait, which is that certain type of function trait. At this point, we've seen several ways of using patterns, but patterns don't work the same in every place we can use them. In some places, the patterns must be irrefutable. In other circumstances, they can be refutable. We'll discuss these two concepts next. So like this is an interesting pattern, and I'm still not used to it myself, but I've been sort of like working on it with, for example, in JavaScript, destructuring in the function signature as opposed to doing it on the very next line. And it allows for some very interesting things with promises in JavaScript. So I'm kind of wondering whether or not there's going to be some interesting things that we'll be able to do with that that might like clean up the code. So the only way I'm going to be able to like work with that would be actually build stuff with Rust and just look out for times we can do that. However, until then, let's go ahead and clean up here. I'm going to want to update where we're at, and this time I want to actually do it properly. Yesterday I forgot to actually do the push, apparently. So where are we? So open up code here and get the README. All right, so currently at, this is updated. You are updated as well. Uh, okay, so save from here, and now onto chapter 18. We'll push on up. That took a significantly longer time than I thought code would do to do that good push. Let's go ahead and make sure that actually got up here. So I have, all right, perfect. So it did work. And tomorrow morning we'll be able to continue where we're at. So is there anything else that I need to update? I don't think there is. So basically we're on to chapter 18. I know there's 20 chapters and then there's that appendix. I'm not sure whether or not we'll like go fully through that. However, it did hint that there's a section in appendix for macros that there wasn't in maybe the rest of the book, so that might be super interesting. And then chapter 20 is going to be that project that we're going to work on, the web server. So I'm looking forward to all of those things. However, it is about 8 o'clock, so I'm going to go get ready for the rest of my day. Thank you, everybody, for stopping by and watching me this morning. I'm going to also, right after this, push this video up to YouTube to archive it, and then I'll be back tomorrow morning at 7 a.m. Mountain Time to continue chapter 18. And who knows, if it's as fast as it looks like, as it feels like, we might be able to get on to chapter 19 tomorrow too. With that, I hope that you all have a great rest of your day, and I'll see you tomorrow morning.